Hello, welcome to Econometrics Melody. In this video, we will discuss about the Bayes formula or Bayes theorem. In our previous video, we had discussed about the conditional probability. So first of all, let us quickly review the conditional probability. So in conditional probability of AB is equal to, if we know the information of A, then we use that information in order to update the probability of other event B. Alternatively, if we know the information of B, then we use that information in order to update the probability of A. So from this relationship, we can find what is the conditional probability of A, what is the probability of A condition on B. Here we assume that we know B, so in that case, probability of AB, we divide it by, and we know something about B. Similarly, the conditional probability of B, when we know A, that is the probability of B condition on A, that is equal to probability of AB. AB refers to A intersection B, and we divide it by the probability of A. So we have seen about conditional probability, and now let us talk about the Bayes formula. So Bayes formula is nothing new. In place of probability of A intersection B, we substitute the value from this relationship. Here we know B, and that is why we substitute the information of A over here, and here we know A, that is why we substitute the information of B over here. So let us focus on probability of A condition on B. So probability of A condition on B is equals to, now here we know B, now let us substitute it with the information of A. We know A over here, into probability of B when we know A, this is probability of A intersection B, and divided by probability of B, because we know B over here. Similarly, when probability of B when we know A, so this is equal to, here we know A, so let us start off with probability of B. We are acting as if we know B over here, and the probability of A when we know B divided by probability of A. Now we will expand the probability of B in two ways, and let us see. So this is all about our Bayes formula. This is the formula for probability, calculating probability of A condition on B, and this is the formula for calculating probability of B condition on A. Now we are going to expand this denominator part, and we are trying to expand it. There are two conditions that we'll discuss over here. The first one, so here let me explain the Venn diagram. The set A contains AB, elements AB, and set B contains element BC, and A union B complement contains the element D. Our A complement is anything that is not equal to A, so that is equals to CD, and B complement is anything that is not equal to B, so it is AD over here, and A intersection B is B, and A intersection B complement, so our B complement is AD, and A intersection is our A only, and then B A complement, so our B is BC and A complement is CD, so the intersection part it is C only. So A union A complement, so A is AB and then A complement is CD, so this constitutes of entire universal set. Similarly, B union B complement is equals to universal set. Similarly, we can, if we write it as A minus B union A minus B complement, that should also be equal to our universal set. Now let us say we are going to write B. So B constitute of these two elements, B and C. So B is equals to, in set notation, first of all, this intersecting part B is equals to A intersection B, that is AB, and then union this part C is equals to B A complement, so it is B A complement. And if we write it in terms of probability, so probability of B, this is equals to probability of AB union can be written as or B A complement, so this is equal to, if we apply our addition rule, so probability of AB or is equivalent to plus, and probability of B A complement. So this is equal to, so the conditional probability, this is equal to, let us act as if we know the information on A. So probability of A into probability of B condition on A plus the same thing over here, probability of A complement into probability of B when we know A complement. So this is what we mean by B. Similarly, we could have expanded A intersection B, that is A intersection B, and union. So we are writing A, and that is everything of A, but that does not belong to B. Now if you look at this, probability of A and probability of A complement, they sum up to 1. So that is why probability of B is actually the weighted average of the conditional probability of B when we know A, and probability of B that does not include A. Now let us write the base formula for this condition that we have already seen in our previous section. Therefore, probability of A condition on B, this is equal to probability of A and then probability of B condition on A, and we divide it with by the probability of B. Now this is equal to probability of A into probability of B condition on A divided by probability of B. We can expand using this relationship, so we write it as probability of A into probability of B condition on A plus, and then probability of A complement into probability of B condition on A complement. So this is the conditional probability of A when we know B. Now let us explore the other condition. Condition number second, we partition the A into many exclusive events such that the sum of the parts is equals to the whole. So this is our event A and this is our event B. So here A is equals to the union of, let me write it as AI, where I is equals to 1 to n, and for our example it is 1 to 6. They are mutually exclusive because we don't have the region called AI AJ. This is equal to 0. No overlapping. So given that I is not equal to J, these segments or the parts of A, they are not overlapping. Similarly, what is the value of B in this case? So we can find B by using union of 1, I is equals to 1 to n. For our example, it is 6, and we have B, and then we intersect it with the value of AI, meaning thereby, so this region, this is called as A1 intersection B, and this region A2 intersection B, and so on. And if we add these regions, that will give us B. When we calculate, so let us calculate the probability for that. So what is the probability of B? And they are mutually exclusive events as well. We don't see any overlapping region in B as well as in the parts of A as well. So let us apply the probability rule for this B. Probability of B, this is equal to, so when there is union, so we add them. So this is the addition of the probability of B and AI, where I is equal to 1 to n, where n is equals to 6 for our case. So if we expand it for this region, this will be probability of B is equal to, so for this particular example there are 6 number of partitions, so this is equal to this relationship. If there are n number of partitions, then we can write it as probability of B is equals to probability of A1 B plus all the way to probability of A and B. Therefore, probability of B can be written as, now let's use the summation rule that we have used already. I is equals to 1 to n, and then probability of this is equals to probability of B AI. Now if we expand probability of BA is probability of A into probability of B when we know A, if we expand it in this way, then we see that probability of B is equal to summation of I is equals to 1 to n, and then probability of AI into probability of B condition on AI. Now let us substitute the value of probability B in our Bayes formula and we will get this result. According to our Bayes formula, probability of A condition on B, this is equal to probability of A into probability of B condition on A, and we divide it by the probability of B. Now we can further expand this probability of B. So this is equal to probability of A into probability of B condition on A, and we divide it by probability of B. So the probability of B in our first case, it was equal to probability of A into probability of B condition on A plus probability of A complement into probability of B condition on A complement. So this, we substituted the value of B using this formula. This was our first case. In our second case, let us say what is the probability of getting AI when we know B. So this is equal to probability of AI into probability of B condition on AI and divided by summation of probability of AI into probability of B condition on AI, where I ranges from 1 to n. So this was for the first condition, and this formula it is for the second condition, and they are similar depending on how we expand the probability of B. So probability of B in the first case we expanded using this relationship, the A, and there were two conditions, A and A complement were there, and in the second case we had partitioned A into n number of segments in such a way that the sum of the parts were equal to the whole, and B was somewhere like this. So external it was A and internal it was B. Let us expand this formula. If n is equals to 3, then how do we calculate it? Let us say probability of getting A1 when we know that the information about B. So this is equals to probability of getting A1 into probability of B, we know A1, divided by probability of A1 into probability of B, we know A1, plus probability of A2 into probability of B, we know A2, after plus probability of A3 into probability of B when we know A3. And similarly we can calculate probability of A2 when we know B, and probability of A3 when we know B, using the same formula. Simply in place of 1 we replace 2 in this case, and in place of 1 we replace by 3 in this case. So this is the main Bayes concept of the Bayes formula. This is very useful, and we substituted the probability of B in two different ways. So in the first case we collected B from the region of A, and then we collected the region of B that didn't belong to A. And in the second case we divide event A into n mutually exclusive parts, and we collect the B from each part. So this is it for this tutorial. Thank you very much for your time. Thank you very much, Econometrics Melody.